Okay, we're on part 2 of hacking the Coco computer's serial output into Arduino. So today we have the Arduino hooked up from the RS-232. We have a clock signal going to our logic analyzer, and this is the circuit. So last time we hooked up the Coco to a Schmidt trigger. So it could be any gate you want, hex inverter, doesn't matter, NAND. And we read our signals. Today we're putting it in the Arduino, and we're also putting a clock out to the logic analyzer. So first up, we're going to see how fast the Arduino can run. So all we're doing here is digital write 8-1, put a high, do a read, put a low. So let's see what that gives us on the logic analyzer. So the top one is our 8 data bits, the 0 start bit, our 8 data bits, and a stop bit. And the bottom one here is our Arduino cycling. So it's a lot faster. Let's zoom in. Okay, so we're getting between 7 microseconds. Now we know the Coco was putting out 1.6 milliseconds. So it's about 177 times faster than the Coco signal. So let's go back to our Arduino. Oh, forget this program. Write a new program. So first up, we're going to check when the pin goes low, and then we're going to do a read. And then we're going to do a delay. We're going to burn off 177 cycles. So we've uploaded that. Now we're going to scan, put some data on the Coco. Here we go. There's our data packet. Let's go find it over here. Okay, so we slowed down the Arduino pulses. Here are the 10 pulses I put on the Arduino. This time I put a delay of 177 on it. Now, we're out of sync. We're trailing off over here. We're not lined up. We really want to take a sample near the middle of each pulse. So that would be our sample point at the start here. And we're way off. Let's go over here and fix the math. A little bit of trial and error. I'm going to upload this to the board. Done. Let's go back here. Take a sample. Voila, there's our data packet. So we're using a pulse viewer, SIGROC, on the little logic analyzer clone. Let's see what we got now. Okay. Now we have a pulse lining up to read the data. Our start bit, our stop bit. And if we look closely at our Arduino cycle, we're going to see something special here. So here's our Arduino signal. Here's the first high pulse. Here's where I do the read. And here's the burning off of the 115 free cycles. So this little dip here, we put that in so we can know exactly where we're reading our data. So what is our data? Let's take a look. We'll start with this one. We have a 1. This one represents a 0, 0. So let's write it down. 1, 0, 0. 1, 0, 0. 1, 0, 0. 1, 1. And that's our start bit, which we're going to ignore. So that looks like that. So we have hex 9, 3. Hex. So let's look at the Coco and let's see what kind of data we were sending out. Our first data was hex 5.5. Our second data was hex 9.3, which matches that. And if we look here at our our first data, we're not counting this one, that's our stop bit. So we have a 0, 1, 0, 1, 0, 1, 0, 1, which is hex 5.5. Now there's better ways on the Arduino to input UART signals, but this is a hack. Assuming we know nothing about what's going on, we're just going to match it. We don't actually need output pulses on the Arduino to read this data. Now we can just use our reads and we could not do them, but it's a lot easier to look on the logic analyzer and have an output pulse. So next up, we're going to take this information and send it out on I2C devices and start doing some cool stuff.